So are we going now then?
Yep.
All right. Welcome to Political Science 370, Social Science Research Methods. This is the lecture that we are having to kind of get us through the rest of the material before I start focusing on specific student presentations and the methodological issues that have come up as a result of those presentations. So, number one, hello everybody. It's I know this isn't ideal. I'd love if we were in class together, but this is the way we're gonna have to do things. So, okay. So I sent out an email with the essay test, and after I did that, I realized I should probably go over a couple more assumptions of O.L.S. so that you guys are ready for that. Okay, so let's go over the ones we've discussed so far. First, O.L.S. assumes that there is a linear relationship between your independent variables and your dependent variables. We discussed that. So that's a really important assumption of O.L.S. O.L.S. assumes that there's a linear relationship between your independent variables and your dependent variables. And it will actually impose linear assumptions on your data. That's what it does. The next assumption of O.L.S. is that you have a normally distributed dependent variable. So something like SAT scores or IQ or some variable that is normally distributed. If it's normally distributed, you can use it as a dependent variable in O.L.S. and it should work just fine. Again, we discussed situations when you do not have a normally distributed dependent variable. The most common situation when you do not have a normally distributed dependent variable is when you have a dichotomous dependent variable. So that's a variable that's coded 1 if the characteristic or attribute is present, 0 otherwise. So, did you vote? Coded 1 if you voted, 0 otherwise. Very common in the social sciences to have a dichotomous dependent variable. And so if you have a dichotomous dependent variable, you should use low-jitter probit. That's the most common solution. And those are just different types of multivariate regression analysis. Okay, the next thing we did discuss this, was O.L.S. assumes exogeneity. That means that your independent variables influence your dependent variable, not the other way around. So if your dependent variable is heavily influencing one or more of your independent variables, then you have an endogeneity problem. And you need to correct for that. Okay. Now, like I said, based on an email I got the other day, I realized, there's one thing I should make clear, and that is, basically, in general, O.L.S. assumes that you are using a random sample, a simple random sample, if you want to call it that, but, a random sample, to estimate the population characteristics, to obtain those coefficient estimates. So O.L.S. assumes you are using a simple random sample, not some other kind of sample. So what's another kind of sample that we discussed? A cluster sample. That's really common with education data. So the researchers will randomly sample from all 50 states, say 5 states. Then within those 5 states, they'll randomly sample schools, and then they'll randomly sample kids within those schools. So you go down level. That's how cluster samples work. Now, let me show you the problem Just one of the problems. When you have a sample that's different from a simple random sample, like a cluster sample. Say we have SAT scores as our dependent variable, like we always have, because I don't want to come up with different ones each time, because I want you focusing on the concept, not the different dependent variable. And say we have parental socioeconomic status and all the usual suspects here, right? Okay. So, say this is our model. SAT scores. How am I getting it on here? Can you see that? And parental socioeconomic status as one of the independent variables, and then other independent variables, as illustrated by the lines there, right? Mm-hmm. Okay, and they're the usual suspects, right? Meaning instructional expenditures per pupil, teacher qualifications, those types of things, tax base, usual suspects, right?
Yeah.
Okay. Now say that a school makes it in to your data set that's downwind from a lead manufacturing plant. Okay? Okay, where are all those gonna be? Below where my model predicts where they will be, or above where my model predicts they will be?
Below.
Below. Why are they all below?
Because they're getting lead poisoning.
we shouldn't laugh, but yeah, they're downwind from a lead manufacturing plant, right? And so you see the problem with a cluster sample is if there's something about this school, well, the students in this school, that isn't in your model, then your data is going to kind of be messed up, right?
Yeah. And
so what is that going to affect? Will that affect your coefficient estimate?
Yeah.
Yes, absolutely. Will that affect your standard errors?
Mm-hmm.
Yes, absolutely. And so those are two biggest things. And standard errors is one of the biggies with the cluster sample.
Yeah.
And other problems. And so the researchers will say, we corrected for the fact that they used a cluster sample by da-da-da-da-da-da. And they'll tell you what they did to correct for the fact that they used a cluster sample rather than a simple random sample. So you guys will run into that. Some of you may in your papers, right? So don't be thrown off by that. So what the heck are they talking about? What they're talking about is the fact that they're not using a simple random sample, right? And that leads to problems. It leads to all kinds of problems, which again, if you take more advanced methods courses or go to graduate school, you'll study those. But the thing I want you to know is whenever you deviate from a simple random sample, there are going to be problems, right? Okay, so that takes me to my own research. I like, to be honest, right? Think back to my own research. And my son is here. He's in our class, so he can answer this. What state were all of our school districts from in my research?
Texas.
Texas, that's right. You guys were born in Texas. You know, we were at Texas A&M. You know, I didn't drive all over the country. I just used Texas school districts. Is that a problem?
Yeah, I guess.
Absolutely, it's a problem. But the thing is, until you can do better, right? Then it's the best we have, and we didn't have the resources to travel all over the country. And remember, we had that data set that was gathered by the state of Texas. We merged it with that superintendent survey, and so realistically, Texas, we had to pick a state, and Texas was the best state to pick because it is racially and particularly racially, but in other demographic ways, it is now where the rest of the country is going to be in 20 years type of a thing. You know, just in terms of the racial and ethnic mix. So, statistically, is it a concern that we didn't use a simple random sample drawn from the entire nation? Yeah, it's a concern. But again, we did the best with the data we had.
Yeah.
So, you move forward. Okay, next. Next assumption of O.L.S. is what is called homoskedasticity. And you can pause this if you need to. Homoskedasticity.
Got it.
Right? And I'm sure a lot of jokes have been made about this over the years. Right? But homoskedasticity. What it is, so this is an assumption of O.L.S. Homoskedasticity. And what it is roughly, remember in statistics it's always roughly or generally, right? But it's roughly equal error variance across observations, right? So, let's just illustrate this using what we already had here. Okay, now remember the distance from the regression line to each observation is your error, right? That's your residual, right? So it's sometimes called the error, it's sometimes called the residual, but it's just the distance from where the model predicts an observation will be and where it actually is, right? Okay, so as you look at this, just eyeball this, as you go from bottom to top, do you have roughly equal error variance across observations? So we have parental status here. And we're controlling for everything else. So when we control for everything else, we'll just put this one up to show where the residual is compared to where it's supposed to be. Is that roughly equal?
Sure.
Yeah, exactly. Statistically, that's close. That's close, right? Now, say instead we get something like this. Remember, each one of these is a data point, even though I'm doing this quickly and butchering it. Okay. Okay. Now take a look at that. What do you see? Just tell me in your own words what you see there.
Well, early on, all the observations are like really close to the regression line, and then later they're really far from it.
Exactly. So, for some reason, my model is predicting really well when parental socioeconomic status is low.
Yeah.
Right? Really well.
Yeah.
But then when parental socioeconomic status is high, not so well.
Yeah.
It's all over the place, right?
Yeah.
Okay, well, first let's discuss what this is called. This is called heteroskedasticity. So, heteroskedasticity. And what this is it's unequal error variance across observations. It's also some other things. There are other methodological problems involved with heteroskedasticity.
Yeah.
But for this course, the important thing, and the thing I want you to get, kind of, is the idea that it's unequal error variance across observations.
So what's happened? Like, have new variables been introduced once like your socioeconomic status crosses a certain threshold? Right? Why is it?
Well, see, that's the thing is that let me make it a little different. So it looks like that. Okay, so that's a really good question, Michael. So let me put this another way. Are you ready?
Yeah.
Is there something about high socioeconomic status households or parents that we don't understand?
I guess so, yeah.
I guess so. Exactly. That's why our model's not predicting very well for them, right? So, is this... What kind of problem is this really then?
Just a lack of variables. You don't include enough in your model. Yeah.
It is a modeling problem. Exactly.
Yeah.
So the London School of Economics will say heteroskedasticity is a modeling problem. It's a model specification problem. It means theoretically you don't know enough about these high parental households to have included that in your model. So that's the problem.
Got ya.
Right? And so you need to go back to the theoretical drawing board in ways and figure out what you're missing. Because you're predicting low SES households and their SAT scores really well. What's going on in high parental? I don't know. Are the kids taking vacations? Are they Paris Hilton?
Yeah.
No offense, no liability law there. Online now, but Paris Hilton's usually the example I use. But I mean, I don't know what she got on the SAT.
Yeah.
But I know if you have $1 million, how much incentive do you have to do well on the SAT?
I don't know.
I don't know either. I don't know. And so, these are probably, yeah, I don't know. I'll just leave it at that before I get into liability issues. But but it may be you reach a point where you have so much money, the normal rules don't apply and you're missing something that's not in your model, right? Okay, so now here's the thing when you have a heteroskedasticity problem. And if you're using O.L.S, I can just guarantee you they almost always have a heteroskedasticity problem, right? And the researchers will address it. And they said we corrected for it by using like White's standard errors or robust standard errors or something else like that. And I don't want to blow your minds too much. This isn't an advanced course. This is an introductory course. But the thing is, there's a concern there that you're just using kind of statistical fixes for what's really a theoretical problem.
Oh.
A model specification problem. You know, the presence of heteroskedasticity lets you know you're missing something. And so what is that? Maybe that's what you should be focusing on. But then again, if we knew what it was, we would have included it, right? Yeah. So again, it's you can't be too hard on researchers when they correct for heteroskedasticity using, like I said, robust standard errors or whatever it is. Because if they knew what variable to include to make their models more accurate, they would. Usually. Mostly. All right. So any questions on that?
Nope.
Okay. So heteroskedasticity makes sense. You guys got it? Okay. So let's go now then to something that's going to come up in your research, and that is a multicollinearity problem. Multicollinearity problem. Multicollinearity problem. Okay. Now, okay. Let's just discuss collinearity first. Collinearity. Some variables tend to rise or fall together. Right? A good example of that is education and income. So, in general, do people of higher education levels make more money?
Yeah.
Yes, definitely. In general, right? And so, a lot of variables are going to be collinear, right?
Yeah.
When you have a multicollinearity problem is when you have a lot of variables that are really collinear or two variables that are almost perfectly collinear, and what that leads to is unstable coefficient estimates and sometimes it makes it harder to get statistical significance. Okay, so let's just stick with, again, the same thing we have all semester. SAT scores, low to high, low to high. And let's say we have, and this is each individual kid's SAT scores and parental education and parental income. Okay, now, so there we are. Let's discuss kids, SAT scores, parental education, parental income. That's what it would look like. And now let's put this down and just think for a moment. Okay? Let's talk for a minute about what it means to hold something constant. Say we're holding parental education level constant, right? So I have two families, and the mom and dad are both doctors, right? Okay. Okay, so I'm holding education level constant, right? Okay, now, how much is this family of doctors going to make? Mom and dad are both doctors. How much money are they going to make? A ton. How much is this family, mom and dad are both doctors, how much money are they going to make? A ton, right? Okay, so now that I'm holding education level constant, I want to look at the effect of income on SAT scores. But the thing is, now that I'm holding education level constant, how much variation am I getting on income? None. Well, very little, right? Very little, right? Because if both husband and wife are doctors in both families, they're both going to be making a lot of money, right? And so this is kind of one of the limitations of O.L.S. compared to true experiments, right?
Yeah.
In true experiments, who manipulates the treatment? Who applies the treatment?
The experimenters, the researcher.
The experimenter, the researcher, absolutely, right? So that's how I make sure you have received the treatment, right? And then I look at the treatment's effect on any particular outcome, right? With O.L.S., we're just counting on stuff varying naturally. Well, you are. You're kind of, honestly, as a statistician, I'm hoping for poor doctors out there, because then that will help me study the effect of income on the dependent variable a lot better if I have variation on that independent variable. But if I have two families of doctors and they're both making the same amount of money, then how much variation do I have on that independent variable? Income. Zero. Exactly. Yeah. Right? And if one makes $1 more, well, that's not enough variation to really get an accurate estimate there, right?
Yeah.
And so, what does the multicollinearity problem lead to? It leads to, like I said, unstable coefficient estimates, because if you gathered another data set of a similar size, you'd run into the same problem and get really different estimates, coefficient estimates. Mm-hmm. And it sometimes makes it really hard to find statistical significance, because your standard errors are going to be really big a lot of the time, because the data, they just don't vary enough for you to have a lot of statistical leverage, right? Okay, so since this is a video and you can rewind it if you need to, a lot of methodologists will say multicollinearity is actually a micronumerosity problem. Micronumerosity problem. And what does that mean? It means you don't have enough numbers. Your data set's not big enough. Once you control for certain things, you don't have enough variation. Right?
Mm-hmm.
So, once you frame it as a micronumerosity problem, what's one of the possible solutions?
Bigger sample size.
Gather more data. Outstanding. Absolutely. Right? And so, if multicollinearity becomes, if you suspect it's a problem, it looks like you're going to need a larger data set. You're going to need a larger sample size. Absolutely. Excellent. Right? And when I was in graduate school, my professor, hard-hitting guy, he said, well, the problem with that answer is, if there was more data out there, then why didn't you gather it already, you lazy bum? Good point. So that's there's more data available. Why didn't you gather it, you lazy bum? I always like that answer. Okay, what else can you do? Okay, see how parental education and parental income are separate here?
Yeah.
Right. If you have multicollinearity problem and these are so collinear that they're leading to the problems we discussed, unstable coefficient estimates, large standard errors, then some researchers will combine the collinear items into an index. So what do parental education, income, and occupational prestige usually get combined into?
Socioeconomic status.
Socioeconomic status, exactly, right? And so, to avoid the multicollinearity problem, some researchers will just combine the variables that are really collinear into an index, right? And then you're more likely to get statistical significance. And your coefficient estimates are probably more stable and more accurate, right? The problem with that is, just from a substantive standpoint, now that you've combined it into an index, it's hard to know the substantive impact that the index is having. Because it's all combined, it's hard to know the substantive impact that it's having on the dependent variable, right? Whereas if I leave them separate, if my data set's large enough and I'm getting really accurate estimates and I leave them separate, then I can say for each additional year of parental education, it leads to an increase of 50 points on kids' SAT scores, right? We're recording right now. So, a really straightforward interpretation, right? Or for every additional $10,000 in parental income, it leads to an increase of 40 points on kids' SAT scores, right? If I leave them separate.
Yeah.
But if I combine them into an index, education, income, occupational prestige, classic SES, then all I can say is, well, an increase of this much SES led to this much of an increase in SAT scores. And which part was it? Was it the education? Was it the income? Was it the occupational prestige? You don't know, because you combined them into an index. You lost in ways you lost information.
Yeah.
Make sense?
Yeah. Now, one question, kinda. So, occupational prestige, isn't that like the only one that is collinear? Because like you could have like high income but low occupational prestige, right?
Yeah.
Okay. But education and income are really collinear.
Really collinear.
Okay.
These are the classic collinear examples.
Okay.
Right. Now, there's one more thing, and this is really technical and probably beyond the course, but if you have perfect collinearity between two variables, it messes everything up. Just so you know. But most researchers are aware of that, and it shouldn't. Don't worry about it. So any questions on that?
No.
Okay. Here's the other thing you can do. Here's one more thing you can do, and it's kind of a no-no, but Another thing you can do is run an underspecified model, right? So like just leave parental income out.
That seems a little cowardly though, doesn't it?
Well, yeah, absolutely. But the thing is, if I eliminate parental income, right? If I eliminate parental income, and I have the usual suspects, but I eliminate parental income, will parental education come back statistically significant?
Yeah.
Yeah, definitely. Yep. Because it's picking up a lot of the variation from parental income also. Now imagine I get rid of parental education and I have parental income and all the usual suspects, right? Will parental income come back statistically significant?
Yeah.
Yeah, probably. Okay, now, you ready for, like, the mind bender?
Yeah.
Really see if you understand a lot of this stuff? Okay? And this is kind of like old school statistics, but I like it. It's kind of old school. If I get rid of parental income and include parental education and the usual suspects, right? So I get rid of parental income and my R squared does not go down much at all. What does that tell you about parental income?
I guess it has no impact on SAT scores, or no, because that doesn't seem to make sense. Oh, education levels predicting the effects of parental income already, or
yeah.
Oh.
Yeah, in a way, yeah. So some people say if you run an underspecified model, remove one, then the other, and then include them both. Okay? Where should your R squared be highest? With one, with the other, or both? When's your R squared going to be highest?
Both, you think?
Both. Absolutely. Both.
Yeah.
R squared can only go up when you include variables. Right? It can only go up. Right? But kind of old school statistics, if, say we have an R square of really good, say 0.90, right? We're just really predicting SAT scores well. Say we have an R square of 0.90, and then we remove parental education, and we get an R squared of 0.89, and then we remove parental income and include parental education, and we get an R squared of 0.89. It lets you know that those two together.
Yeah.
And then we take them both out, and it goes down to like 0.5.
Okay.
You know what I mean? So you can start tinkering with it. That gets kind of advanced. But do you understand what I mean by that? Say we take them both out, and our R squared goes from 0.9 to 0.52, right?
Yeah.
What's just happened? Our R squared's gone from 0.9 to 0.52 when we get rid of these two variables.
We're not accurately predicting the variation in the dependent variable.
Exactly. Yeah. Have we lost a lot of explanatory power by removing these two variables?
Yeah.
Yes, exactly. And so that's why, if you include parental education, then it takes you up to 0.89. If you take it out and then include parental income, it takes you up to 0.88. You include them both, and it takes you to 0.90. It's a sign they're really collinear, and they're really helping your model predict the dependent variable a lot better. You really need them. Yeah, so the possibility exists, if you engage in another hypothetical for a minute, see if you really understand this.
Okay.
The possibility exists, your R squared could go up, by just including these two, right? We leave these two out, and our R squared is like 0.50, right? We include these two, and it jumps to like 0.9, but neither one is statistically significant. What would you conclude?
They're collinear.
We have a collinearity problem.
Yeah.
Right? Because look what just happened to my R squared. It massively increased the predictive ability of my model.
Yeah.
Right? But these aren't coming back statistically significant? And it's because they're too collinear. Make sense? Yeah. So it's an interesting problem in its own right, and it's also a nice little instructional tool just to kind of help students understand what's going on, I think, a little better. Hopefully it helps. Make sense? Okay, so now let me show you something you have seen earlier in the semester. But now you're smarter. Now you have more information. You're better able to judge things. Okay, this was a discrete choice model. There we go. Can you help me, Michael? I'm right. There we go.
I got it. Okay.
Okay, there we go. Discrete choice model of Rehnquist majority opinion assignments. Okay, Michael, so you can see this. Let's go down this.
Yeah.
Ideology. Well, and look at the bottom. We got stars, whether they're statistically significant or not. So just keep that in mind. We got stars. Okay, so remember, this model is predicting who William Rehnquist will assign the majority opinion to. And there's 9 justices on the U.S. Supreme Court, right?
Yeah.
And ideology was measured as ideological proximity to the Chief Justice. So how close you were to the Chief Justice ideologically.
Okay.
Right? So what did they conclude? What effect does ideology have on whether Rehnquist assigns you the Supreme Court opinion or not? None. Exactly. Then they have one variable times another. What's that called?
Interaction variable.
That's an interaction term or an interaction variable. Exactly. So there was consensus times ideology. What effect does that have on the probability that he will assign you the majority opinion? None. Minimum winning coalition. You had 5 justices. Bare majority. Right? Times ideology, another interaction term. What effect does that have on the probability that you will get the opinion assignment?
It's a positive.
Positive. Increases probability. Absolutely. What about important case times ideology?
Nothing.
No effect. Important case times the chief?
No effect.
No effect. Equity. You already have been assigned a number of cases.
Definitely negatively correlated. Yeah.
Right. Reduces probability you'll get the next opinion assigned to you. Exactly. Expertise. You have written a number of opinions in this area already, like Stephen Breyer in administrative law.
Increases.
Increases. Efficiency. You're known for writing opinions quickly.
No effect.
No effect. End of term times efficiency.
Increases.
The probability you'll be assigned the opinion. Absolutely. Okay, and then log likelihood they have, number of observations, that's their N, 2,213. Okay, so what did we as a class conclude about what affects Rehnquist's opinion assignments after this? Ideology or institutional constraints?
Institutional constraints. Yeah.
Exactly. Like equity and that type of thing.
Yeah.
Okay. Now, guess what is highly collinear with ideology?
I don't know.
Really?
Yeah, this. Well, I'm trying to figure it out. Is it consensus times ideology? Is it
And?
ideology? What? What?
Guess what's really collinear with ideology? Ideology times something else.
Important?
You literally have it in here 1, 2, 3, 4 times.
Oh. Okay.
Okay.
Gotcha.
Okay, so is a concern that you may have a collinearity problem.
Yeah.
Yeah, absolutely. See, and they're trying to make the argument, oh, ideology doesn't matter. It's more institutional constraints, right?
Yeah.
But then they've included ideology 4 times.
So did they purposely create a multicollinearity problem, or?
You tell me.
I don't know.
Exactly. That's why now the guys who did this research, they do good stuff.
Okay.
And they said they didn't have a collinearity problem. But you as a reader need to be cautious about that, right? Because if I were trying to show that ideology doesn't matter, this is how I would do it.
Yeah.
You know, you know what I mean?
Yeah.
I just introduced so much collinearity that it would come back not statistically significant.
That's kind of sleazy, though.
Well, no. Like I said, the people who did this...
Yeah, I mean, if you're in other situations.
Yes, yeah. Absolutely. Absolutely. Make sense?
Yeah.
Okay. The other 2 terms, very quickly, that were in the book that we haven't gone over, emic focus and etic focus. They're in the book, so make sure you know them. Just emic focus is when the researchers put things in the subject's terms, and the setting in the subject terms, and an etic focus is when the researchers put things in the researcher's terms. Hope you guys are doing well. From here on out, I'll more be responding to journal articles that are out there, or papers that you guys submit. Remember, you guys are no longer responsible for doing a class presentation. You just do your paper, and then you'll need 10 pages of reactions to these videos, and we'll get through the semester. Hope you guys are doing well. Okay, take care. Bye-bye.
Idiot.